So, to understand what we mean by compiler optimizations, first we need to know what we mean by compilation, okay? And one definition of a compiler is a computer program that transforms code written in one programming language into another programming language, okay? This is a very generic, broad definition and is, I think, a good definition for our working purposes, because it conveys a lot of useful information. First is, there is a program that you have to deal with, somebody has written this program and you are going to be using this compiler. But the important part is, what does it do? It takes code that has been written in one programming language and converts it into another programming language, okay? That is what a normal compiler does. It would take something like the C code that you write and convert it into the machine code that can run on a processor. It becomes an executable file. So, over there it is sort of easier to understand what it means by take one programming language, that is C, and convert it into another one which is machine code, because we still think of machine code as a programming language. But what we are interested in is creating hardware, okay, which is why it makes sense to think of hardware as something that can itself be described by means of a programming language. Of course, we know what the language is. In our case, we are probably going to use Verilog, but the idea is that, you know, anything that can be put down into a systematic set of instructions or steps is all that we mean when we talk about a programming language, right. So, with that in mind, this definition is very broad, of course, but is also, you know, it conveys the right meaning for the way that we are going to use it. Input, of course, for a compiler could be a number of different types of languages, any programming language that we are typically familiar with. C is probably the first language that we come across which requires compilation, or Java, depending on whether you did that C or Java in school, C, C++ or Java in school, right. Python is a slightly different beast. Python is one of a class of languages called interpreted languages, right. MATLAB, Python, Perl, Ruby, a whole bunch of different languages fall in this category. Now, even though they are interpreted, at the end of the day, what is still happening is that you are writing code in one language and underlying it there is some conversion to another language or another set of instructions that can execute on the processor. So, even though it is called an interpreter because of the nature of how it runs, the fact is that it is still doing the same thing, it is converting code in one language to another language, okay. So, there is some compilation involved even with Python. Of course, the point is, instead of any of these languages, you could also have a hardware description language, Verilog or VHDL being the most common ones, or as we are seeing in this course, you can take C and treat it as a hardware description language in some ways, okay. So, what is the output? Once again, it is a programming language. The usual common outputs, one is the machine code of the processor, which is the most common case. The second is intermediate byte code. This is, for example, what is generated by Java, right. Java generates something called a byte code, which is then run through the Java virtual machine and is actually executed, right. That is somewhere in between the actual machine language of the processor and a high level language like C or Java. Or the third kind of output could be a gate level netlist, right, which is what finally we are interested in. What I am leaving unsaid over here is the fact that you could also have something which takes input in C and outputs Java, that is also a compiler, right, but those are rare, they are not really very useful in most cases. So, what is the compilation process? Again, this is something that you probably should have some familiarity with. If some of you have taken a course in the computer science department, then you would probably have gone through the entire process of building a compiler. If not, then at least the basic stages are something that you need to be aware of, right. Broadly, you can split it into three parts: the front end, the middle portion and the back end, okay. Very innovative names, but whatever. The front end, all that it does is take your input, the C or HDL code. The first step is something called parsing. Alright, so the parser, what it does is splits the input into so called tokens, right. So, tokens are essentially parts of your programming language which essentially correspond to keywords or structure. So, for example, when I write a line like for I is equal to 0, I less than n, I plus plus, for is one token, it is a keyword which is understood by the C programming language. The parentheses are also tokens, I is a token which is translated as a variable, the equal sign is a token which is translated as an initialization, the 0 is a token which is translated as the value to initialize, and so on. Okay. Next we come to grammar analysis, right, which is the so called syntax checking, which essentially says, is this a meaningful sentence in this language that you have written. Okay. Once both of these have passed, that is to say you are able to recognize this as a language, as a program that has been written in C, and it is valid C, there is no syntax error that has been detected. What the front end does is generate something called an intermediate representation, an IR. Okay. There are many different kinds of intermediate representation. If you look at them, ultimately they will resemble to a large extent the assembly language that you might be familiar with from a basic course on microprocessors. Okay. They resemble that, but they are not exactly that, for one simple reason. Right now you still do not know which processor you are going to run on, you do not care, right. This is still generic, it is independent of the processor target or the actual, whether it is going to be a processor or whether it is going to be hardware. The middle portion is the one that does a lot of the different kinds of optimizations on the code, right. It basically takes the intermediate representation that has been generated and modifies it in various ways, right. What are those modifications? We will look at many of the modifications. Of course, we will not be looking at IR, we will not be looking at intermediate representations, because that is generally hard to understand. So, I will be explaining all the optimizations with regard to a generic C type of language, but the meaning and how it applies to the case of intermediate representation should be fairly clear. The back end does something called code generation, right. In the case of a C compiler, a compiler that is going to run on a processor, it will generate the output executable files, right. So, the ELF file that I used in order to demonstrate the FFT code running on the system, that ELF file is essentially something that is created by the C compiler for the ARM processor and essentially consists of a set of machine instructions. Similarly, Vivado HLS generates a different kind of code. It does not generate machine instructions, it generates netlist in the form of Verilog code, synthesizable Verilog code. Okay. At this point, a few more optimizations are done, which are target dependent, because the back end is something that is generating code for a very specific target, which means that, for example, if I know that I am targeting a processor that has 2 multipliers, I can do certain kinds of optimizations that may not otherwise be possible on a processor that does not have 2 hardware multiplication units. Okay. Now, one thing to keep in mind, even the so called target independent optimizations, many of them, as we will see later, they make certain assumptions on the general type of target that we are going to be aiming for, right. In particular, they will make certain, some of the optimizations work only if you have a certain type of memory layout, if you have a certain cache structure, if you have a certain basic ALU behavior, some number of registers, and the fact that the number of registers is at least so much, or at least one hardware multiplier is present, those kind of things change the kind of even the target independent optimizations that we can talk about. There are a few general guidelines that are applied across compilers. One of the most obvious ones when you think about it, but a lot of people, and the reason why I am putting these guidelines over here is very often I find that people try to start optimizing code. They write code and then they start making optimizations. One of the things that you need to understand properly is how good is your compiler, the compiler that you are going to use. Do you really need to write the optimizations on your own, or can you rely on the compiler to apply them properly for you, right? And more to the point, if you try to apply the optimizations by yourself, are you in some cases actually preventing the compiler from exploring more options and possibly coming up with something even better than you thought of? Okay. In general, of course, these are more generic guidelines. The first and foremost is optimize the so called common case. What do I mean by the common case? What we are talking about over here is there is a certain kind of a set of paths through the program, right. Typically there will be some for loops as well as other instructions that are being executed. Some of them are common, they are executed a large number of times, whereas there are others that are only going to be executed a small number of times, but might consist of a large block of code. Okay. does it make sense to optimize those, the ones that are not going to be commonly executed, or does it make sense to optimize only the ones that are commonly executed? So, optimize the common case, essentially what it is saying is, if you are starting from some part of the program, it then has to run through multiple things, and there is some loop over here that is going to run many times, and there are other things over there that are going to run only for a small amount of time, right. What you need to do is actually measure the total time that is going to be taken by this and find the part which is occupying the maximum amount of time and see whether you can reduce that. Okay. If you can reduce this part of the program, then it actually makes sense, because after that whatever you have, even if this remains exactly the same as what it was earlier, what you end up with is shorter runtime, right. There is in fact a way of phrasing this, it is called Amdahl's law, or this is one possible way of interpreting something called Amdahl's law, right, which essentially says, the Amdahl's law is slightly different, but what it says is, if you have a program that takes some X amount of time and you are able to accelerate some part of it, even if you can get infinite acceleration on some part of it, you are still limited by what remains. Okay. So, of course, if you go and concentrate on a part that takes a very small amount of time to start with, then the overall benefit that you get as far as the program is concerned is very small. Okay. Now, the next set of steps, avoid redundancy. This seems like general good common sense, right. You do not want to have redundant code, the same code happening again and again. Why am I putting this exception over here? Because there are cases where it makes sense to recompute things, right. It might actually be faster for you to recompute certain values or to redo a certain part of the code, rather than trying to optimize it and make it some efficient function call which has a high overhead associated with it because of the way that it gets called. Okay. Same story for less code. You might find that if I can create a few functions and call them repeatedly, that everything is great, but there can be situations where actually expanding out the code and writing it out more explicitly rather than trying to make it more compact can make it actually easier and faster for the computer to execute. We will actually see some examples of that going forward, but in general those are the exceptions. As a general rule, less code is good. One important thing which again is related to what I said about the compiler independent things still needing, or rather target independent things still needing to know something about the target, is this thing which says you need to be aware of what your memory layout looks like. More than the memory layout, what I mean is the cache structure, right. So, typically what happens is you have some large amount of DRAM, a small L3 cache, an even smaller L2 cache, and a really tiny L1 cache. Why I am saying tiny is, this could be gigabytes, this could be tens of megabytes, this would be 1 to 2 megabytes, and this would be kilobyte in a typical processor. The speed with which you can access data written into those blocks of memory is inversely proportional to the size of the memory, right. So, the smaller ones can be accessed faster in general. This actually makes a significant difference to how efficient your program becomes. So, you need to be aware of that when you are doing compilation. There is finally this concept of parallelism, which once again we will need to understand quite well, because in our case parallelism is even more of a concern than for general compilers that target CPUs, because in CPUs at most you have a very limited amount of parallelism because your processing units are quite less, whereas in hardware potentially you can create as much parallelism as you want. Okay, how do you make use of that? Of course, it is a trade off, because the more parallelism that you have, more hardware that you are using, or more instructions are being used in software at the same time. One very important requirement is that as far as possible your optimizations should be guided by profiling. Once you have identified that your function is actually a bottleneck in some way, then yes, it makes sense to go in and try to optimize it. Okay? But unless you do this kind of profile guided optimization, most compilers by their nature do not do that. The compiler optimizations that we are going to talk about are not going to be doing this, right. They just have some general guidelines on what kind of optimizations can be applied, and they will try to apply them in any way possible. But when you are trying to make further improvements upon the code, you should actually target the functions or the areas of your code that are actually slow and take a large amount of time. Okay? Warning, premature optimization, right? Invariably, in fact, it's very likely that you yourself are going to want to do this, in the sense that the moment you see the code, you immediately think, okay, yeah, I can apply this kind of either pipelining over here or this kind of unrolling over here, right? Or do some other kind of optimization with some variables that I have. Do not do any such thing until you understand the impact on the entire program or the entire system that you are going to implement. Because very often what happens is, you think that you are modifying your code in a certain way to improve it, that unfortunately ends up making it harder for the compiler to apply other kinds of optimizations that it could have. And by applying certain optimizations early on in the process, you might be preventing certain things that could be done later. Okay? So you should always keep that in mind. You need to actually understand the big picture. What is your overall code getting translated into before you start applying any optimizations?